In this video, I'm going to go over the solutions to exam practice session 1. So in this first problem, we're trying to figure out what values of h of b will make h admissible. So first, let's go over what the definition of an admissible heuristic. So an admissible heuristic is one such that h of x, the heuristic of that state, never overestimates the cost from that state to the goal, which we'll denote as h star of x, and also that h of x is always non-negative. So in this case, we're concerned with h of b, and so we need to determine h star of b. And h star of b is the cost from state b up here to the goal. And we can see that the shortest path from b to the goal is 12, which is the path from b to c to d to f to g. So therefore, h of b must be less than or equal to 12 and greater than or equal to 0. In part B, we're trying to determine what values of h of b will make h a consistent heuristic. So what we need to do is ensure that for every pair of nodes in the graph, the difference in the heuristic between those two nodes never overestimates the cost between those two nodes. So therefore, we should check all of the neighbors of b. So let's start with the neighbor a. So if we have h of a minus h of b, that should be less than or equal to the cost from a to b. And similarly, since each edge can be traversed in both directions, we also know that h of b minus h of a should be less than or equal to the cost from b to a. So in this case, h of a is equal to 10. H of b is what we're concerned with, and the cost from a to b is 1. And similarly over here, we have h of b minus 10 is less than or equal to 1. So this first inequality yields h of b greater than or equal to 9 and h of b less than or equal to 11. Okay, now let's consider the next neighbor of b. So let's pick c. We know that the difference in the heuristic between b and c should be less than or equal to the cost from b to c. And also that since the cost from b to c is equal to the cost from c to b, we also know that h of c minus h of b should be less than or equal to the same cost from c to b. And that cost in this case is 1. H of c is 9. So h of b minus 9 should be less than or equal to 1. So that gives us h of b is less than or equal to 10. And this one gives us 9 minus h of b is less than or equal to 1. H of b is greater than or equal to 8. Lastly, we're going to consider the node d, because that's the last neighbor of b. So h of b minus h of d is less than or equal to the cost from b to d. So that means that h of b minus 7 is less than or equal to 5. And similarly, the other way, h of d, which is 7, minus h of b, should be less than or equal to the cost from d to b, which is 5. This top inequality gives us h of b is less than or equal to 12, and this bottom gives us h of b is greater than or equal to 2. So looking at all these inequalities, we can combine them. The largest lower bound on these between 2, 8, and 9 is going to be 9, and the smallest upper bound on h of b between 11, 10, and 12 is going to be 10. So therefore, the final answer is that h of b must be less than or equal to 10 and greater than or equal to 9. Also note that we didn't need to check the nodes that are not neighbors of b, because if we know that this heuristic is consistent for every other pair of nodes that doesn't include b, and if, for example, d to f is consistent, then and b to d is consistent, then we also know that b to f is also consistent, because the cost from b to the difference in heuristics between b and d doesn't overestimate the cost, and neither does the difference in heuristics between d and f. So therefore, combining those two, the difference in heuristics from b to f must not overestimate the total cost from b to f. Now let's move on to part C. So in this problem, we're trying to determine what values of h of b will cause A star graph search to expand node A, node C, node B, and then node D. So in this case, in this graph, we always start by expanding node A. So that's a given, and we don't need to worry about that. And so when we expand node A, we get the two nodes that are next to A, which are B and C. And the cost to B is 1, and the cost to C is 4. Next, we need to check the case in which when node C will be expanded before node B, and what values of h of b will make that true, and when node B will be expanded before node C. So in A star search, nodes are expanded by the f function, which is equal to g of n plus h of n, where g of n is the cumulative cost and h of n is the heuristic of that node. So for node C to be expanded before node B, we know that f of C must be less than f of B, and so therefore g of C, which we know is 4, which is just the cost from A to C, plus the heuristic of C must be less than f of B, which is 1, the cumulative cost to B, plus h of B. And we know h of C is equal to 9, so therefore h of B must be greater than 13 minus 1, which is 12. So now we know that node C has just been expanded before node B, and we should check now the two successors of node C, which are B and D. So we can add those to our search tree. So we'll put B, and I'll put a prime here to indicate that it's different than the other state B, and D. And the cost to B in this case was 1, and the cost to D in the graph is 3. So now we're concerned with when will node B be expanded next before node D. And there's two cases in which node B can be expanded. The first is through the path A to B, and the second is through the path C to B. And we know that this path A to B is always going to be expanded first, because f of B is equal to g of B, which in this case is 1, plus h of B, compared to f of B prime is equal to the cumulative cost to B prime, which is 5, plus h of B. And we know that f of B, let's clean this up a little bit, is always less than f of b prime because 1 plus h of b is always going to be less than 5 plus h of b. So now we only need to concern ourselves with this state here. And the only time in which node B will be expanded before node D is if f of b, which equals 1 plus h of b, is less than f of d, which is and I'm also going to put an equal signs here because we know that ties are broken alphabetically, so if they're equal, we know that b will be expanded before d. So in this case, f of d is equal to the cumulative cost to node d, which is 7, plus the heuristic for d, h of d, which is also 7. And we're interested in the case when 1 plus h of b is less than or equal to 7 plus 7. And this gives us h of b is less than or equal to 13. So overall, we get the condition that for a star graph search to expand the nodes in this order, h of b must be less than or equal to 13 and greater than 12. In this problem, we're trying to determine if two search algorithms are equivalent under certain conditions. So in the first question, we're trying to compare uniform cost search with breadth first search using cost dij. And note that breadth first search doesn't care about the costs, and it just expands nodes using the shallowest node in its fringe. And uniform cost search is a cost-sensitive search, and it does use those cost dij. So in this first case, where dij equals 0, uniform cost search is always going to expand nodes by tie-breaking because the cumulative cost is always going to be 0 regardless of the path. So the path that uniform cost search is going to return here is just going to be A, B, C, etc., because ties are broken alphabetically. Whereas breadth first search is going to expand nodes and find a different path depending on the, he's going to expand nodes in a different, Breadth first search, on the other hand, is going to expand nodes in the order based on shallowest nodes first and the deeper nodes at the end of the search. So we know that this is not true. In the second case, we're looking at when all of the edges are constant value alpha for a positive value of alpha. So let's consider a search tree that starts here and expands to a bunch of states. And the cost to each of these states is alpha. And then as you add on more states, the cost of these states are also alpha. So the cumulative cost of all of the nodes in the first level is going to be alpha, and the cumulative cost of all of the nodes in the second depth level is going to be 2 alpha. So in this case, uniform cost search will expand nodes and take nodes off of the fringe based on their lowest cumulative cost. So therefore, it will expand all the nodes in the first depth first because all of these have a value of alpha, then all of the nodes in the second depth second because all of these have a value of 2 alpha, and so on and so forth in future depths. And that's just identical to breadth first search. So therefore, uniform cost search is equivalent to breadth first search for a constant weight value alpha that is positive. Similarly, when dij equals 1, that's just a special case when alpha equals 1. So we know that this is also true. Note that when alpha is negative, if we make all of these negative, then the reverse happens. So in this case, the value of the nodes on the fringe in the first depth is going to be negative alpha. The value of all the nodes in the second tree level is going to be negative 2 alpha, and so on and so forth. So in this case, uniform cost search is going to expand nodes with the lowest cumulative cost, and that's going to be the deepest node in its search tree, or the deepest state that has been reached. This is exactly what depth first search does, and not breadth first search does. So we know that these two answers are not true. So as we just stated, a value of alpha for these costs is going to produce the same result for uniform cost search as depth first search. So we know that these are both true. We also know that since this is the same as breadth first search, this is going to expand nodes in a different order than depth first search. And similarly to above, when Dij equals 0, we know that uniform cost search is just going to return nodes alphabetically just by tie breaking, whereas depth first search will return something different based on the structure of that graph. So we know that this is also not a correct answer. Moving on to problem 3, we're now comparing uniform cost search on a graph with weights Dij between node I and node j versus uniform cost search on a graph with cost Cij. Remember that uniform cost search takes nodes off of its fringe by calculating the sum of all of the edge weights, all of the costs in a particular path. So you're summing over all of the edges in your path. So now we're going to be looking for a case when this sum over Cij is going to be give you a similar or the same ordering over edges as when you use weights Dij. So let's first consider this second one. If we set Dij to be equal to 1 over Cij, this is going to make the larger weights smaller and the smaller weights larger. So therefore, the order of expansion of Cij versus Dij is going to be different because smaller values of Dij will correspond to larger values of Cij. So we know that this is not an answer. All these other ones, Cij increases with Dij. So we now need to narrow these down and look more closely at what they do. Let's first start with this third answer, where Dij increases at a rate alpha with Cij. In this case, when we set Dij to be equal to alpha times Dij, then we'll get the sum of alpha Cij. And so this is going to be equal to alpha times the sum of Cij. Since alpha is greater than 0, we know that then when we compare this to the order of nodes expanded in the first graph, that these are going to be expanded in the same order, because if you just scale all of the possible options in your fringe and their values, then the ordering isn't going to change. So therefore, this is a correct answer. Now let's look at these next two cases in which we add a constant value to Dij. In this case, the value of a node in the fringe is going to be the sum of, In this case, the value of the node in the fringe is going to be the sum of Cij plus alpha. And this is going to be equal to the sum of Cij, and then once you take alpha out of the sum, so put this in parentheses, It's going to be plus n corresponding to the path, so the number of nodes in that path, times alpha. And so therefore this value in your fringe is going to depend on the number of nodes in the path. For example, if you're starting from state A and there's a path here from state A to the goal, and each of these have weight 1, versus a single path right here, and this has weight 4. If this is your original graph with weights Cij, then your new graph with weights Dij is going to have a value of 1 plus alpha for each of these edges, versus this edge will have a weight of 4 plus alpha. So if alpha is something like 1, this path right here is going to have a cost now of 6, versus this cost up here will have a cost of 5, which makes this the optimal path on this graph, versus in this graph, the original graph, this is going to be the optimal path. So when you add a constant factor, it's unfairly penalizing longer paths that have more edges in them. So therefore, this is not going to yield the correct, the same path, an equivalent path between running uniform cost search on both of these graphs. Now let's look at this first answer. So when Dij is equal to Cij squared, some edges are going to be scaled more than others based on the value of that edge. For example, if you have 2 nodes that have weight 40, 2 nodes that have weight 40 versus 1 node that has weight 70, and this is your goal, and this is your start. Then in this original graph, the best way to go is to take 70. However, in your new graph with Dij, these values are now going to be 1600, and this will be 1600, and this path is going to be 4900. And so in this case, where before it was optimal to take the 70, in this new graph, it now is optimal to take these 2 edges, 1600, because 1600 plus 1600 is 3200, which is less than 4900. So therefore, these uniform cost search on the 2 different graphs is not equivalent. And note that in both of these examples, I use the fact that uniform cost search always returns the optimal solution for a graph with weights. Next, let's consider uniform cost search versus greedy search. So let's remind ourselves, uniform cost search is going to be taking nodes off the fringe based on its fringe strategy by calculating the sum of the cumulative cost to that node, which is going to be the sum of Dij in this case, versus greedy search uses the value of the heuristic at the last node in its path. So now we want to consider, when is the ordering of nodes in the fringe going to be the same under the sum Dij versus when we use the function h of n. Note that in this case, this notation is denoting that if we have an edge from I to j, then this is the Dij is the weight from I to j. And then this sum is going to be over all edges in a particular path that's on your fringe that you're looking to expand. So it'll be the weight of this edge from I to j plus Dij plus Dij plus Dij. And then, so therefore, if you set Dij to be h of I minus h of j, that's the heuristic of the first node minus the heuristic of the second node for each edge. And then the weight of this edge, dij, would be the heuristic of this node minus the heuristic of this node, and so on and so forth for the rest of the path. So first, let's calculate dij, what it would be for this first option right here. So if we were adding up dij, where dij is equal to h of I minus h of j, this is option A, we would get the sum of h of I minus h of j. So note that in this case, we're always adding the first node of the edge and subtracting the second node. And then for the next one, we're adding the first node and subtracting the second, adding the first, subtracting the second. So at each time, we're going to cancel out what was subtracted at the previous term in the sum by adding that term to the sum. So what this is going to give you is h of the start minus h of n, which is going to be our last node. So this is node n right here. So note that if we compare this value, which is how uniform cost search is determining what to pull off the fringe, versus what greedy search is using, this is actually the negative of what greedy search is using plus some constant h start, which is the first node in your search tree. So in this case, it's actually going to pull nodes off of the fringe in the reverse order that greedy search would use. Uniform cost search is going to be doing the reverse. So this is not, they're not equivalent in this case. Next, if we consider when dij is equal to hj minus hi, we're going to have the sum of dij is going to be equal to sum of hj minus hi. In this case, so we're adding each time the second node of the edge, subtracting the first node, then adding the second, subtracting the first. So in this case, all the nodes are going to be canceling out again, and what we're going to be left with is the last node, h of n, minus the heuristic of the start node, which is h of start. In this case, the order of nodes in the fringe is going to be determined by h of n because h of start is just a constant. So this is going to be the same as what greedy search is returning. So in this case, greedy search is equivalent to uniform cost search. So now let's consider this third case, case C. In this case, the sum of dij is going to be the sum of alpha hi. So in this case, uniform cost search is going to be summing up all of the heuristics up to node n and multiplying it by alpha. We can clearly see that this is not going to always give the same answer as h of n. We can also show a quick counterexample for this. So say you have some start node A, and it has two options. The heuristic of A is 5, and the heuristic of these two nodes is 2 and 1. And therefore, since dij is equal to alpha times h of I, the weight of this node is going to be 5 alpha, as is the weight of this node. In this case, uniform cost search will return the node based on a tie-breaking scheme, whichever one comes earlier in the alphabet. So if we say that this is A, then or say that this is B, because A is right here, then uniform cost search will choose B over C, because B comes first in the alphabet. Whereas greedy search will choose whichever has the lower heuristic value, which in this case is C, because 1 is less than 2. So we've just shown that dij is not, when equal to alpha times h of a, is not equivalent to uniform cost search. Now let's consider part D, where we have dij is equal to alpha times h of j. So in this case, the sum of dij is going to be equal to alpha times h of j. And if we compare this to h of n, what uniform cost search is doing is it's using all of the heuristics on its path and summing it, and it's using that that value to determine which node to expand off of the fringe next. Whereas the greedy search is only using the last heuristic value n to determine what to expand next. So this is can definitely be different in different cases, but we can also look at a counterexample again in this case. It's not going to be, this counterexample is not going to be as simple as this past case, because if you only look at one time step, then h of j is going to equal h of n. So let's consider the case where we start at a node A, and then we have a node right here that has a heuristic of 101, and then the goal, versus down here when we have a node with a heuristic of 100, and then a node with a heuristic of 99, and a node with a heuristic of 98, and then go to the goal. In this case, the first node expanded in both cases is going to be 100, because 100 is less than 101. Then after we expand 100, greedy search is going to expand 99, because 99 is less than the alternative 101. However, uniform cost search is going to sum all of the h of j's and multiply by some alpha. So uniform cost search will compare 101, which is on the fringe, to 100 plus 99 times, and both of these are multiplied by some value alpha. And since 101 is less than 100 plus 99, or 199, uniform cost search will then expand 101, whereas greedy search will expand 99. So this is also not a correct solution. And in this last case, dij is equal to cij plus h of j plus h of I. So this is case E. And so the sum and how uniform cost search is going to determine how to select nodes off the fringe. It's going to sum cij plus h of j plus h of I. And in this case, this is going to be just like the other cases in C and D. None of the h of i's or h of j's are going to cancel out because they're all positive. And this is definitely not going to be give a same ordering as h of n. So this is also not a solution in which uniform cost search will be equivalent to greedy search. Now let's move on to the last part of part D, comparing uniform cost search to A-star search. So in this case, what we're interested in is A-star search, which uses the costs Cij, and this is your term G of n plus H of n to expand nodes, versus uniform cost search uses sum over dij. This problem is actually quite similar to the previous problem in that when we determine dij, we want it to have the same ordering as sum of cij plus h of n. So we want something in which the heuristics won't add up, but they will cancel out, so that we're just left with h of n rather than a sum over the heuristics. So if we try this last value and we set, this is option E, if we set dij equal to cij plus h of j minus h of I, we're going to get the sum over cij plus h of j minus h of I. Then for each term of the sum, the h of j is going to cancel out with the h of I at the next time step. So what we're going to be left with is the sum over cij plus h of n minus h of the start. So if we have a bunch of nodes in our fringe and they're all have this value, they're all going to be, the ordering is going to be determined by this part because this is just a constant. So therefore, this must be equivalent to what A star will give you. So this is a correct solution. The previous solution will instead return the negative of this, h of star minus h of n. So this is not correct. Similar to the reasoning why problem A wasn't correct in part I. And then for these two cases, this is just going to sum up the heuristic values on the path rather than just using the last value of the heuristic as with these two. So therefore, this is the only solution.